Today we are discussing the engineering backbone of our connected world, the foundations that hold telecommunication towers upright. This is not just about concrete and steel. It's about safety, stability, and network reliability. These towers, ranging from 30 to over 300 meters tall, carry the antennas that give us mobile service, broadcast, and data. Their single most critical component is what you don't see, the foundation. Its sole purpose is to act as the ultimate anchor. It must safely transfer all the forces acting on the tower, its own immense weight, the weight of equipment and ice, the pressure of maintenance crews, and, most critically, the massive horizontal push from wind and seismic activity deep into the ground. A foundation failure is catastrophic. It leads to network blackouts, poses a severe public safety hazard, and results in enormous financial loss. Therefore, its design is a non-negotiable exercise in precision engineering, balancing absolute safety with cost-effectiveness. To understand the foundation, we must first understand what it supports. There are several primary tower types, each with unique characteristics that dictate the foundation approach. First, we have self-supporting towers. These are the familiar ladder structures you often see in rural areas. They can be unguyed, standing freely on their own base, or guyed, supported by tension cables anchored to the ground. The foundation for a guyed tower must resist tremendous pull from those cables. Next, the sleek monopole, a single, tapered steel tube common in urban and suburban settings. Its foundation must handle a very high bending moment, like the root of a giant flagpole. We also have traditional lattice masts, and finally, rooftop-mounted structures on buildings, which present their own unique load transfer challenges to the existing structure. The key takeaway here is, one foundation design does not fit all. The choice between a massive spread footing, deep piles, or rock anchors is dictated first by the type of tower we are building. We break down the critical selection factors. How do we choose between the foundations we just discussed? The decision largely depends on three constraints: base width, soil type, and environmental context. First, look at base width. If your tower is wide, specifically greater than 4 meters, you are generally limited to pad and chimney or concrete auger foundations. For narrower towers under 4 meters, raft foundations are suitable, provided the soil is sandy or gravelly. Second is soil and subsurface conditions. If you encounter black cotton soil, loose clay, or a standard penetration test value less than 5, you must use pile foundations. Conversely, if you are in hilly terrain with hard rock where deep excavation is impossible, rock anchors are the only viable choice, requiring only about 1 meter of chiseling. Finally, consider operational constraints. If the tower is temporary, intended for service for less than 10 years, steel grillage is the preferred choice because it can be dismantled and reused. Additionally, for irregular terrain where legs need to be at different heights, pad and chimney is your best option, whereas raft foundations fail here because they strictly require perfectly flat ground. We have the pad and chimney foundation. This is the standard choice for gravel or non-cohesive soils. It relies on 3 main components to transfer the load: the stub which connects to the tower leg, the chimney or pedestal, and the bottom pad. Depending on the specific structural needs, we can adapt this design into 4 subtypes: plain concrete, reinforced concrete, stepped footings, which must keep an inclination below 40 degrees, or pyramidal footings, which are excellent for resisting punching shear. The key takeaway for this type is its flexibility. It is the best option when you are dealing with irregular ground levels requiring leg extensions. Moving directly to slide 3, we look at the concrete auger or caisson foundation. While this is also for large base widths greater than 4 meters, it is a specialized well-type foundation used when environmental conditions are difficult, specifically where there is soil erosion, settlement issues, or even underwater requirements. These structures can be circular shafts, square, or pneumatic caissons. While they offer superior stability by reducing vibrations and effectively transferring axial tension and compression, you must keep in mind that they are significantly more expensive and time-consuming to build, requiring heavy machinery and special equipment compared to the standard pad and chimney. Let's look at the steel grillage foundation. This system is built using steel I-beams, H-profiles, or channels arranged in tiers directly below the tower legs. This specific design is the go-to choice for two scenarios. First, in low-bearing soil beds, and second, for short-term projects where the tower is intended to be in service for 10 years or less. The primary advantage here is logistics. Because it requires shallow excavation of only 1 to 1.5 meters, the steel components can be easily dismantled and reused at a new location after the project ends. While timber was once a material option for grillage, we now avoid it due to grain structure limitations, preferring steel or precast concrete. However, you must account for the high cost of steel consumption and the necessity of site welding and corrosion treatment for the metal buried in the soil. Next, we have the pile foundation, which is the heavy-duty solution for difficult environments. If you are working with black cotton soil, loose clay, or any soil with a standard penetration test value of 5 or less, you must use piles. This is also the standard for offshore transmission lines or sites where bedrock is not found within a 5-meter depth. The mechanism here relies on transferring high tension and compression loads deep into the earth through both skin friction and end bearing on hard strata. A critical structural element is the pile cap, which ties a group of piles, often 4 or more, together to support the chimney. While this method provides superior stability and lateral resistance, it is important to note that it has the highest construction cost and duration, requiring complex machinery to execute. Finally, we have rock anchors, which are specifically designed for hilly areas composed of hard rock where traditional deep excavation is impossible. Instead of digging a deep pit, we perform chiseling to a shallow depth of just 1 to 1.5 meters. The stability comes from tendons, steel bars that are anchored directly into the bedrock using chemical or concrete grout. These anchors can be installed vertically or at an incline depending on the rock structure. The main advantage is the significant reduction in earthwork and formwork. We only need formwork for the chimney and the small interface with the rock. However, similar to piles, this method requires special drilling apparatus to install the tendons effectively. In this final comparative matrix, we summarize how to choose the right foundation based on 3 key variables: base width, soil condition, and execution constraints. First, look at base width. If your tower is wider than 4 meters, your primary choice is pad and chimney, which offers flexibility for irregular terrain. However, if you face underwater conditions or heavy erosion with that same width, you must switch to concrete auger or caissoons. For narrower towers under 4 meters, raft foundations are excellent for stability against overturning, but they strictly require flat ground. Second, consider extreme soil conditions. If you are on hard rock in hilly terrain, rock anchors are the most efficient, requiring minimal excavation. Conversely, for weak black cotton soil or offshore sites where bedrock is deep, pile foundations are mandatory, despite having the highest construction cost. Finally, for time constraints, if the tower is temporary, standing for less than 10 years, steel grillage is the only logical choice. It allows for quick dismantling and reuse, trading concrete volume for higher steel consumption. To conclude our presentation, we move from design to site execution. Once the foundation type is selected, the physical work begins with site leveling. As seen in field operations, this involves clearing vegetation and using excavators, JCBs, to cut slopes and create a flat plot level, as soil often cannot be stored on site. After casting the foundation, curing is critical. The concrete must be kept wet to achieve strength. Once the civil work finishes, the site requires perimeter fencing, which is mandatory for safety and radiation protection, generally set 2 meters from the antennas. Finally, the site is equipped with grounding systems, orange pipes, lightning arresters, and aviation lights. Whether it is a 40-meter tower or a smaller structure, the process ends with painting, installing gates, and ensuring the battery banks and SMPS systems are secure, resulting in a fully operational telecom site.